Chapter 7 uses Chapter 6 as its foundation. Chapter 7 helps to apply Chapter 6. Your test will be over both Chapters 6 and 7. We begin, though, looking at some gems, sapphires, rubies, things that are often made into jewelry. And once we find these things naturally in the environment, in various places, under different types of conditions, then oftentimes, as you might imagine, we see if we can duplicate them, synthetic, if we can make them ourselves following the pattern and using the kinds of conditions that under which these things form in the environment. So we can ask this question, a theology question, who made sapphires? And of course, ultimately the answer is God. More interestingly, as far as science is concerned, is not just who made it, but how did he make it? Did he just speak them into existence immediately, or did he use a process by which they formed? Both of them require a sovereign God with incredible ingenuity and artistry and design. And for the sake of science, oftentimes we like to discover how does God do the things that he does. Remember, science does not explain away God. Science explains the way that God does what he does when it comes to the natural environment, the universe, everything in nature. So one of the things that's interesting is when we do things synthetically, sometimes they look kind of sterile or they're a little bit boring. They don't have some of the intricacy and beauty that they have in the way that we find them in nature. So coming down here, rubies and sapphires. Notice the sentence says they are just aluminum oxide with traces of impurities. Now, anytime you see the word just or merely, you want to be very, very careful. The term is often used to oversimplify the complexity or structure of something. And certainly there is a pattern of aluminum and oxygen atoms. But does that mean it is just aluminum? It's just aluminum and oxygen. The very fact that these patterns can form require all kinds of things that we would call laws and principles that govern not just the structure of ions and atoms, but also the way in which they connect together, which is what this chapter is going to be honing in on. And the fact that there are impurities, oftentimes we use the word impurity as something to be avoided. We don't want impurities in our food or in our beverages or in our air. But this word impurity here is actually what gives the gemstone its beauty. And again, that shows that in the organizational structure that God uses when he creates things, according to specific patterns and designs and processes, that he also was very interested not just in their function, but in their form, or we could say their beauty. There was a famous architect named Franklin Lloyd Wright, and his houses were supposed to have form and function. They were supposed to be practical, but at the same time beautiful. And that's what we strive for often in our engineering and in our inventions, is to not just have something that is functional, but we would like it to also have some beauty and some elegance to it. And of course, we say it all the time in creation. And some other things about gemstones, their price depends upon the demand, and people demand a ruby that has color, particularly the more unusual colors. Coming up to here. In fact, if a ruby is not slightly cloudy, in other words, because of impurity, it may be a synthetic stone and much less value. So the ones that we create aren't as valuable as the ones that God has created with whatever processes he has designed. It also helps us to discern what is man-made and what is natural, or we could say God-made. Notice that the rubies come from several very different places around the world. And most recently, as some glaciers have receded, remember the temperature of the planet ebbs and flows. Sometimes it goes higher, sometimes it goes lower. We have proxies that help us to see the fluctuations of the Earth's temperature throughout the millennia. When we look at ice cores, for example, in glaciers and in the other places where there's deep ice, like in the polar caps. We can also look in other places as well. Just tree rings, at least for more recent chronology, we can see ebbing and waning of the Earth's temperature by the amount of growth that takes place. But I mention this because of the fact that all of these minerals, whether it be oil or forests or access to oceans or waterways, deserts, minerals of any type, they are not evenly, randomly distributed throughout the crust of the Earth, but they are concentrated here and there. And oftentimes that becomes the basis for war and aggression when one country, region decides that they want something that another region has. And of course, God's intention for this type of uneven distribution is for people groups and nations to begin to get along, to trade, to begin to develop their own resources, whether it be human resources with innovation and technology and inventions or natural resources. Nations should do everything they can to benefit each other through trade. We've been making rubies synthetically for over a century, and we try to synthesize and make other kinds of things as well. Think of all the plastics and other types of artificially made organic compounds that there are. And we're going to get to that chapter in a little bit. A little bit farther on down, we see that one of the practical reasons why these impurities can fit into crystalline structures of aluminum and oxygen atoms is because the radii are similar. And that's one of the things we're going to be looking at in this chapter, are the various properties that atoms have because of their size and their electronic arrangement. So, we've been talking about the wave mechanical model. Is the electron a particle or is it a wave? So it depends what experiment you're doing. And so we think about the wave mechanical model as being a way to think about both of these things, a particle versus a wave, being true, but we focus on the one that does the best job of explaining the property that we are investigating. And so we think of electrons as being assigned orbitals. That's the third quantum number, which is part of a subshell, which is part of the main energy level, which is the first quantum number. And the orbital is a region of space. This region of space, be it a sphere or a barbell or some other very unusual structure, is a pattern, a regularity, and therefore it can be described by a mathematical equation that gets increasingly complicated as you move from the spheres of the S subshell all the way to the orbitals in the F subshell. And it's where we find the electron 90% of the time, where we have a high probability. Because remember, as soon as you try to identify where the electron is, you actually change where it is in the process. The orbitals arranged in the subshells are what we call, these are parts of these electron shells, three-dimensional shapes. And so we're going to be applying this model to the electronic shape of all the elements, the electronic structure of all the elements. So that we're going to be applying in this chapter what we learned in chapter 6. The second objective is to explore some of the properties of elements. For example, size, electronegativity, ionization energy, things like that, which we'll get to towards the end of the chapter. Those are those periodic trends you might remember from first year chemistry. So these properties are related to their structure. They're directly related to the arrangement of the electrons in the atoms. Remember, our goal in thinking God's thoughts after him is to try to explain the properties that we observe based upon the structure, as far as we understand that structure, of the atoms. Now, we've mentioned the Pauli exclusion principle in passing in the last chapter. And the idea here is that no two electrons for a given atom are going to have exactly the same set of 4 quantum numbers. No two electrons for a given atom will have the same address. That's what makes it exclusive. The address of each electron is exclusive. And so they might be in the same main energy level, quantum number 1, but they could be in different subshells, S, P, D, or F. Well, 2 electrons could be in the same subshell, but they might be in different orbitals, the 3rd quantum number. Well, 2 electrons can be in the same orbital, but only if they have the opposite spin, which is the 4th quantum number. So every orbital, whether it's an S or P or D or F orbital, can only hold 2 electrons if they have opposite spin. And that's a test question that is frequently missed because people are thinking about subshells often instead of orbitals when the question is asked, how many electrons can you put into, let's say, a D orbital? An orbital in the D subshell can only hold 2 electrons if they have an opposite spin, just like an orbital in an F subshell or an orbital in a P or an S subshell. So be careful when you read those test questions. And again, remember that we use these letters to designate the quantum numbers, but we can also just use 1, 2, 3, and 4 for our quantum numbers. Now, one way to represent these electrons and the fact that you can only have 2 electrons in an orbital is to use something called a box with arrows in it. Represent the orbital by a box. Now, no, the orbital is not a box, and only s orbitals are spherical. P orbitals are that barbell shaped, almost, and D orbitals, there's 5 of them. One of them looks like an inside-out donut, and so forth. We can represent them with a box, or we can represent them with a circle. I usually use circles. It's faster to draw than a box. Instead of using an arrow to represent an electron, I just use a slash. And then if I have 2 electrons, I just use 2 slashes, making it X. You can use the box or the circle, but make sure in college you use the one that your professor prefers. So if we're talking about the hydrogen atom with its 1 electron, that 1 electron is in the first energy level. It is in the first and only subshell of that energy level. Remember, you begin the subshell numbers with 0. And it is in the first and only orbital of that subshell. Again, you begin with the number 0. It happens to be spherical. And then its spin, and you can use either the positive or the negative. Typically, we use the plus 1/2 before we add the second electron to the orbital and call it a negative 1/2, but either answer would be correct. You could also have 1, 0, 0, minus 1/2, and that would be the correct address, showing the 4 quantum numbers of a single hydrogen electron. Either one, with the negative or the positive, would be a correct answer. So we have these orbital box diagrams. Then when we move to the second electron in that first energy level, and this would be the helium atom with its 2 electrons. The first one would be this one, the second one would be this one, or we could say the first one is this one and the second one is that one. Doesn't matter. Notice that they're in the same main energy level, the same subshell, the same orbital, but they have opposite spins. And why do we say they have opposite spins? Because opposite spins have opposite magnetic fields, which enable them to attract to help to offset the fact that both being negatively charged, the electrons would repel each other. It's the only way you can get two electrons in an orbital is by having opposite spins. So moving on down, we know that a p subshell can hold a total number of 6 electrons. It has 3 orbitals, so each orbital, like I said before, holds 2 electrons. 3 orbitals, 2 times 3 is 6. 5 orbitals, 5 times 2 is 10. 7 orbitals, 7 times 2 is 14. If you do the math and you plug in your principal quantum number n, the total number of electrons, the maximum number of electrons, can be represented by the equation 2n squared, which means if I have, for example, the third energy level is going to have 3 subshells, S, P, and D, or 0, 1, and 2, and it's going to have 5 orbitals in the D subshell, plus the 3 orbitals in the P subshell, plus the 1 orbital in the S subshell, with 2 electrons per orbital, total number of electrons 2n squared. This is a good time to pause and see if you can do the review and check. Now, this chart right here helps us to see a big picture idea going all the way out to the 6th energy level. And then the number of subshells that are available. Notice that down here we begin to follow the letters of the alphabet, F, G, H, and so forth. Generally speaking, we don't have enough elements on the periodic table to need to use G subshell. And then when we look at the orbitals available, we follow the pattern, 1, 1, 3, 1, 3, 5, 1, 3, 7, and we're just using the odd numbers as we go up. And then you double that to get your total number of electrons, and then the total number of electrons is 2n squared. Now, in this section, we want to understand and predict the distribution of electrons in atoms with many electrons. Remember, we've pretty well figured out, so we think, the hydrogen atom. And you might have noticed there are a few more atoms on the periodic table. I'm looking at one right now. In other words, we know of at least another over 100 atoms. And so things do get increasingly more complicated with more variations. We might call them exceptions to rules, when in fact the exceptions are just what happens to our ordinary understanding of the rules when we don't take into consideration all of the other things that are going on in a very, very complicated atom with many, many electrons and lots of overlapping of these subshells and shells. And we use, when we begin to figure out the electron configuration for a given atom, something called the Aufbau Principle, German word for building up. And so we begin with the electron closest to the nucleus in the first energy level, first subshell, S spherical orbital, and we build outward. We place the electrons as close to the nucleus as possible, where they would be naturally located because it's the most stable configuration. And then when that first energy level is filled, we move out to the second and eventually the third, and we keep going until we run out of electrons. That's the Aufbau Principle. And hopefully you remember that from first year chemistry, but we'll get some practice in. Now, when it comes to the subshells, we begin to find, as we get to bigger and bigger atoms, especially when we move to the fourth energy level, like the row where potassium and calcium are in, that these energy levels begin to overlap. Or we might use another word that is used in chemistry, and that is some of the outer energy levels begin to penetrate into the inner energy levels. And that is simply because, for example, the fourth energy level, S subshell, happens to be a little closer to the nucleus than the outermost D subshell of the third energy level. And there's an overlap there. We would say that the 4s penetrates the 3d, and therefore we add electrons to the fourth energy level, where potassium and calcium are, before we pick up completing the filling of the third energy level, the building up of the third energy level, beginning with scandium, going all the way through zinc. And you can use these, the nomenclatures of N's and L's, where we're adding them together if you want. And I find that to be a little unnecessary. Once you understand the structure of the periodic table, I don't actually use any of these equations like this when I think about the electron structure for a given atom. Now, this picture is trying to show you a little bit of that overlapping or penetration of subshells on each other, and there is no overlap with the first. Notice if the nucleus is down here, the positive pull from that nucleus, the first energy level is closest, the second energy level is farther away, the third energy level, if I try to pick the middle of the third, notice that this distance is much greater than this distance, and if we come up with the fourth up there, that distance is going to be even less. The farther away you get from the nucleus, the closer and closer the main energy levels are to each other. When we spread out the orbitals, like the 2s from the 2p, even though the 2s and the 2p are in the same main energy level as second, and they have the same n plus L, first quantum number plus second quantum number when you add them together, because S is bigger than a 0 for P. That's why we put the 2s closer to the nucleus than the 2p in terms of as we build outward from the nucleus. It's more stable, and rules of thermodynamics and stability rule. Later on, of course, we're going to see that the 4s sort of comes in right there before the 4p and the 4d and so forth because of overlap. Now, this picture over here is interesting, it's clever, and I never use it because it's too much trouble to set up. And the way you do this is you begin by writing down 1s, and then you do 2s, 2p a little higher up, then you do 3s, and then 3p, and 3d, and so forth. And then you say, okay, here's the order in which they're filled. We put our electrons in the first energy level, and then the 2s, and then the 2p, and then the 3s, and the 3d, and here's the overlap right there going into the 4s before we go back and fill up the 3d. And in my mind, it just seems to me to be too much trouble to be worth it, setting up that chart and doing the arrows. I think it's better if you just learn to read the periodic table and follow the elements in order as you see them on the traditional periodic table. And when you get to argon, element number 18 at the end of the third row, and you see that potassium, element number 19, is the beginning of the fourth row, you immediately know you've started the fourth energy level before you finished the third energy level, which is where scandium, element 21, picks up. Just follow the periodic table. Now, the effective nuclear charge is an admission that what I've told you so far is a little bit simplistic, and what you've learned so far about the charges of ions, for example, because of the more electrons or less electrons and the number of protons, it's more complicated than that. So instead of having the theoretical nuclear charge acting on a given electron, we have what we call the real or effective nuclear charge. You might say, for example, that if you have a lithium atom with its 3 protons, every single electron, so if this is my nucleus with its 3 protons, and there are, let's say it's got 7 neutrons, okay, that's the nucleus. And then you've got, let's pick a different color here. You've got 2 electrons in the first energy level. And in the second energy level, let's say you have another electron. You're tempted to say every electron, each one of the 3 dots, is experiencing a +3 pull from the nucleus because of the 3 protons. Well, theoretically that sounds nice, but in effect, this electron way out here is shielded from the nucleus by the 2 electrons in the inner orbital, the inner main energy level. It's kind of shielded, and as a result, it is not quite experiencing the full +3 pull from that nucleus. So if you think about Z as being the atomic number for lithium is 3, and then you subtract the number of core electrons. The core electrons would be the ones in the core, because the one out here is, that is not a core electron, that is a valence electron. So S is a 2, and my effective nuclear charge, 3 minus 2, is 1. So the electron in the outer shell is effectively feeling a +1 pull from the nucleus. It's not feeling a +3 pull from the, like these electrons in the first energy level are experiencing. So what we're trying to do is to take into consideration both the attractive force from the nucleus, but also the fact that the electrons in the inner shells are repelling the other electrons. So it's not just about the attractive force of the nucleus, but also the repulsive force from all of those other electrons that are in the core energy levels. And you're going to see as we go through here that this helps to explain the penetration of outer orbitals into inner orbitals or energy levels, something that we often call overlap. And again, another way of talking about the fact that the electrons that are in the core energy levels are repelling the outer one is that they're screening it. They're screening it from the full impact of that nuclear charge. So that's some of the language that is used. So if we look at this chart down here, you can see that with my atomic number Z, with for element hydrogen, it's a 1. For element helium, it's a 2. Lithium is a 3. And we just keep going up the line here. You can see that as I add protons, which creates the very next element, my value of Z is going to go up because Z is the number of protons, so that's a no-brainer. My value of S is going to go up, which is the number of core electrons, and therefore the value of the effective nuclear charge is going to go up. They are going to be proportional. And you can see this is directly proportional because I have a slope, a straight line, a straight proportionality. Now, when we look at the number of, the number S, the number of core electrons, you can see that the value of S is going to go up also. It's pictured here in green. But when you go from the first row of hydrogen and helium and we jump to the second row, there's a corresponding jump. And then when we go from the end of the second row up to the third row, there's a corresponding jump. And this is because we're starting a whole new energy level, which means that next electron is farther away from the nucleus than the previous 8 or the previous 2 electrons were, and hence the jump. Now, when we do the math, and again, the math is Z minus S to get my effective nuclear charge, that's what you have here in red. And so as your number of electrons increases, thinking right here, when you jump to the next energy level, it drops way down before it increases again. There's a contraction. That effective nuclear charge goes down when you jump out to the next energy level, and then it increases within that energy level, which makes the atom get smaller. And as we get towards the end of the chapter, you're going to see that when we go from left to right on the periodic table, the radius of the atom and the radius of an ion of that atom is going to go down from left to right. And that's all because of the effective nuclear charge. Over here, you can see a graph charting the probability of finding an electron. So, for example, when it comes to finding the probability of the first electron is going to be very, very close to the nucleus. This area represents that. And very, very unlikely you're going to find that first electron, which is so close to the nucleus and under tremendous attraction to that nucleus. You're very unlikely to find it very far away from the nucleus at all. But then when you move to the second energy level and the third electron, you can see that electron is not going to be held in as tightly in place because it's way out here as opposed to in here, and therefore you can find it farther away from that first energy level. The probability goes down that you'll find it in here. And so we can draw some conclusions here. The average charge experienced by the electron is called the effective nuclear charge. In other words, in effect, when you take into consideration the internal core electrons using up, so to speak, some of that positive charge or shielding the outer valence electron from the full effect of the positive charge, repelling that outermost valence electron, we get the effective nuclear charge on that valence electron. And of course, that's going to become very important because it's going to dictate how easy it is to remove an electron from the outer shell, something called the ionization energy, which we'll get to later in this chapter. And the order, the relative to extent to which an outer electron penetrates inner orbitals, S is the most, and then the P, then the D, and then the F outward. So the effective nuclear charge is greater for S electrons because they're closest to the nucleus, experiencing the full brunt of the nuclear pull from the protons. It's greater than the P, and the P is greater than the D, and the D is greater than the F. We can take a look at this chart right here to show that particular trend of the effective nuclear charge. As you go from left to right across the periodic table, you can see it gets greater and greater, shrinking the overall size of the atom.